Hello guys, my name is Mohit and I'm an IIT Kharagpur graduate specializing in data analytics. I have worked with numerous product-based companies and I teach Excel, SQL and Tableau in my YouTube channel named Learn Analytics with Mohit. Before watching my videos, I will request you all to please like, comment and share my videos and subscribe to my channel as this will motivate me more to make future videos. So guys, वेलकम बैक टू माई यूट्यूब चैनल। आप सभी का बहुत बहुत स्वागत है मेरे यूट्यूब चैनल में। फॉर ओल्ड यूजर्स वेलकम अगेन एंड फॉर न्यू यूजर्स वेलकम फॉर द फर्स्ट टाइम। टुडे वी आर गोइंग टू लर्न SQL advanced topics like window functions, subqueries, CTEs. Later, some videos will be on SQL cheat sheet, order of execution of SQL queries, interview questions to practice from Data Lemma, Lead Code and Strata Scratch. Lastly, I will also post SQL questions asked in different companies like MPL, Cars24, Whitehat JR, Zomato, Zepto, EXL, etc. If you find my videos helpful, don't forget to hit the like button and subscribe to my channel.
So let's get started with SQL Advanced. Moving to the next slide, we have window functions. SQL window functions perform calculations across a set of table rows that are related to the current row. Unlike aggregate functions, they do not reduce the number of rows returned. That is, in the case of aggregate functions, we use group by, and the number of rows in the output are reduced. But in the case of window functions, the number of rows are preserved. They do not reduce the number of rows returned. Instead, they add a calculated column to the result set. Row number is the first window function. Definition: assigns a unique number to each row within a partition of a result set ordered by a specified column. Syntax is row number over partition by a column name ordered by column name. So it gives a row number to every row within a partition or without a partition ordered by a particular column. Let's say order by sales, partition by category, row number over partition by category, order by sales. It will, for each category, it will produce a row number. Next slide. Example: assign row numbers to employees grouped by department and ordered by salary. Select employee ID, department ID, salary, row number over partition by department ID, ordered by salary descending as row number from employees. Use cases: identify the top n items per group. If you want to find the top n items, so we can just use a filter called row number less than equal to n. Eliminate duplicates by retaining only the first row. For this, we can use row number less than equal to 1. Rank. This is the second window function. Assigns a rank to each row within a partition. Rows with the same values receive the same rank and the next rank is skipped. Suppose we have the values such as 50,000, 50,000, 30,000 and 20,000. So 50,000 will get one rank, 50,000 will get one rank. Then we have 30,000, it will get, instead of 2, it will get 3 rank, and 20,000 will get 4 rank. So rank 2 is skipped in this case. So this is how rank function works. Rank over partition by column name, order by column name. Rank employees by salary within each department. And select employee ID, department ID, salary. Rank over partition by department ID, order by salary descending as rank from employees. Use cases: determine ranks in competitions or performance metrics, identify ties in order data sets. We have dense rank. Dense rank is similar to rank, but no ranks are skipped for tied rows. So we have similar syntax for dense rank. Coming to the next slide, we have example: dense rank employees by salary within each department. Same query we can use that we use for rank function. Use cases: generate compact rankings without gaps. Useful in reporting scenarios where skipping ranks is undesirable. Next slide, n-tile. Divides the results into n approximately equal parts or buckets and assigns a bucket number to each row. So it basically supports we need quartiles. So quartile, that is 4. So results will be divided into four equal parts, and assigns a bucket number to each row. So every row will get a one. Suppose there are 40 records, and I want entire 4. So every 10 records will get a particular number. So first 10 records will get number 1, next 10 records will get number 2, next 10 records will get number 3, and next 10 records will get number 4. Entire n over partition by column and order by column. Divide employees into 4 salary quartiles. Let employee ID salary entire 4 over order by salary as quartile from employees. Use cases: divide data into quartiles, percentiles or deciles. Groups rows for statistical analysis. Then we have lag function, very important. Returns the value of a column from a specified number of rows before the current row. Returns the value of a column from a specified number of rows before the current row. So suppose we have a current row. Suppose we have sales value in the current row. Okay. Now returns the value of a column from a specified number of rows before the current row. So before the current row, let's say I'm using lag sales comma 1. So just one row before the current row, that value will be returned in the next column, that is lag column. Syntax: lag of column name, offset, we can give any number, default value over partition by column name, order by column name. Example: find the previous month's sales for each month. Select month sales, lag of sales over order by month as previous month sales from sales data. Compare current values with previous values. Use cases: identify trends or changes over time. Lead function returns the value of a column from a specified number of rows after the current row. So lead of column name, find the next month's salary for each month. Find month sales, lead of sales over order by month as next month's salaries, next month's sales from sales data. Compare current values with subsequent values. Instead of previous values, we will compare current values with the subsequent values, forecast future values. First value, returns the first value in an ordered partition. Syntax: first value column name over partition by column name, order by column name. Find the lowest salary in each department. So select employee ID, department ID, salary. First value of salary over partition by department ID, order by salary, ascending as lowest salary from employees. Retrieve initial values in time series data and find starting metrics for a group. Last value, find the highest salary in each department. Select employee ID, department ID, salary. Last value salary over partition by department ID, order by salary, ascending as highest salary from employees. Use cases: retrieve final values in time series data, summarize, and metrics for a group. Now we have cumulative distribution. Calculate the cumulative distribution of a value within a partition. Calculate the cumulative distribution, salary distribution for employees. Select employee ID, salary, cumulative dist over order by salary, ascending as cumulative distribution for employees. Use cases: generate cumulative distribution graphs, analyze percentile ranks. Next we have 10th window function is percent rank. Calculate the relative rank of a row within a partition as a percentage. Find the percentage rank of employees based on their salary. Select employee ID, salary, percent rank over order by salary as percent rank. So this is a summary table of window function, or you can call it cheat sheet. Function row number. Purpose is assign unique row numbers. Use case: eliminate duplicates or rank items uniquely. Rank: assign ranks with gaps for ties, competitions or performance-based ranks. Dense rank: assign ranks without gaps, reporting scenarios with compact rankings. Entile: divide data into n parts, quartiles or percentiles in analysis. Lag: fetch prior row values, time series trends or changes. Lead: fetch subsequent row values, forecasting or comparing next values. First value: fetch the first value in the partition and fetch starting values in time series data. Last value: fetch the last value in the partition, summarize final metrics. Cumulative distribution of calculation. Percent rank, relative rank as a percentage. Now, how to calculate running total, moving averages, and rolling sum using window function. In the case of running total adds the values cumulatively from the first row to the current row. Select order ID, order date, amount, sum of amount over order by order date as running total from sales data. So explanation: sum of amount calculates the cumulative sum. Over order by order date defines the order of rows for cumulative addition. Suppose we have order ID, order date 1, 2, 3, 4, amount and running total. So first row we have 100, next 250 plus 200 450 plus 250 700. Track cumulative revenue over time, calculate progressive totals for financial reporting. These are the use cases. Moving average. A moving average calculates the average of values in a sliding window, typically for the last n rows. So select order ID, order date, amount, average amount over order by order date, rows between two preceding and current row as moving average. In this case, we have explanation: average amount calculates the average. Rows between two preceding and current rows defines a 3-row window, the current row and the two preceding rows. 3-row window moving average. You can change it to 5 preceding, 10 preceding, 20 preceding, 16 preceding, like that. Order ID, we have amount 100, moving average will be 100, plus 150 will be added, so 250 by 2 will be 125, 200 will be added, so 2, 3, 4, 450 by 3, that is 150, no, 250 plus 150, 400 plus 200, 600 by 3, that is 200. Moving average. Analyze trends over a sliding window. Example: stock prices, sales, smooth fluctuations in data for better insights. Next we have rolling sum. Rolling sum is the sum of values within a sliding window, like a moving average, but with sums instead of averages. Select order ID, order date, amount, sum of amount over order by order date, rows between two preceding and current row is rolling sum. Sum of amount calculates the sum of the window. Rows between two preceding and current row defines a 3-row window, the current row and the two preceding rows. In this case, we have 100 and 150 will be added as 250. 200 will be added, so 450, and 250 will be there, 150, 400 to 600, because we're taking two preceding rows. So current row will be 250 and two preceding will be 200 and 150 will be added. Use cases: aggregate stage, sales or revenue over the last 10 days. Analyze performance metrics within a sliding window. Now, keynote rows between clause. Rows between n preceding and current row defines a fixed number of rows before the current row for the sliding window. Rows between unbounded preceding and current row includes all the rows from the start till the current row. Use cases: running totals are used in financial reports and performance metrics. Moving average is crucial for trend analysis. Rolling sums help monitor short-term aggregations. Now, simple window functions cheat sheet. Window functions compute the result based on a sliding window frame, a set of rows that are somehow related to the current row. Aggregate function versus window function. Unlike aggregate function, window function do not collapse rows. In case of aggregate function, as you can see, these three rows are aggregated to a single row, and in case of window function, the three rows are preserved in the output. Partition by divides rows into multiple groups called partitions. To which the window function is applied. Default partition with no partition by clause. The entire result set is the partition. So this is the data. Partition by city. So Paris, we have 300, 500. Total sum is 800 and 800. In this case, we have 439, 7 to 900. And London, we have 500 as a sum. Order by. Specify the order of rows in each partition to which the window function is applied. Default order by. With no order by clause, the order of rows within each partition is arbitrary. Partition by city, order by month. Window frame is a set of rows that are somehow related to the current row. The window frame is evaluated separately within each partition. Rows, range, we have groups between lower bound and upper bound. Partition, n preceding, this is n preceding, n rows, this is current row, and this is n rows, that is n preceding, m rows, that is m following, and total we have unbounded preceding and unbounded following. The bounds can be of the 5 options: unbounded preceding, unbounded following, current row, end preceding, or end following. Lower bound must be before the upper bound. Abbreviations: unbounded preceding between unbounded preceding and current row, and preceding between and preceding and current row and between current row and following between current row and end following, between current row and unbounded following. Default window frame followed by is specified. The frame is arranged between unbounded following preceding and current row. If order by is not specified, frame specification rows between unbounded preceding and unbounded following. Subqueries in SQL. A SQL subquery is a query nested inside another query. It allows you to perform operations in steps by using the result of the subquery as input to the order query. Subqueries can be used in select, where, from, and having clauses. Syntax: select column 1, column 2 from table name, where column name operator. You can give select column 1 from table name, where condition. Single row subqueries, multiple row subqueries, and correlated subqueries. Example: subquery in the where clause. Find employee whose salary is greater than the average salary of the company. So select employee ID, name, salary from employees, where salary greater than select average salary from employees. In the subquery, we will select create, will calculate average salary of the company of all the employees. And in the outer query, we have employee details like employee ID, name, and salary of employee from employees. Explanation: the subquery calculates the average salary. The outer query selects employees with the salaries above the calculated average. In the select clause subquery, display the names of employees along with the department names using a subquery. Select e.name, select d.department name from departments D, where d.department ID equal to e.department ID as department name for employees E. Subquery fetches the department name for each employee based on the department ID. Subquery in the from clause. Find the maximum salary of each department. Select department ID, max salary, and max salary from. Select department ID, salary from employees as department salaries. Group by department ID. Subquery in the from clause deploys a derived table for the auto query. Subquery in the having clause. Find department where the total salary of employees is higher than the average total salary of our department. So first we need to find average total salary of all departments. Okay, so select average total department salary from select department ID sum of salary as total department salary. So select department ID sum of salary as total department salary from employees, group by department ID. This is my inner query. This is my subquery, and selecting average total department salary from this subquery. So department salaries, this subquery, it is select department ID, sum of salary, total of employees, group by department ID as department salaries. So as department salaries is the alias name for this inner subquery, and selecting average of total department salary from this is the outer query of, and calculating having sum of salary. For each in the select query, we have department ID, sum of salary, total salary from employees, group by department ID having sum of salary greater than select average total department salary. So here we got find departments where the total salary employed, that is sum of salary, is higher than the average total salary of all departments, average total department salary. Explanation: inner subquery. The subquery calculates the total salary of each department using sum salary and group the results by department ID. This forms a derived table department salaries. Outer subquery, it calculates the average of all department total salary. Average total department salary is a having clause, filters the departments which actual salary is greater than the average total salary of all departments. Multi-row subquery within operator. Find employees who belong to departments located in New York. Select employee ID name from employees where department ID in. Select department ID from departments where location is equal to New York. The subquery retrieves department IDs where the location is New York. The outer query fetches employees located belonging to those departments. Correlated subquery. Find employees whose salary is greater than the average salary in the department. Select employee ID, employee name, employee salary from employees A, where employee salary greater than select average salary from employees where department ID equal to each department ID. Explanation: the subquery calculates the average salary for the department of each employee. This is a correlated subquery as it depends on the outer query. Use cases of subqueries: complex filtering and conditional selection, creating derived columns, aggregating or calculating results within subsets of data, combining data from multiple tables without joins. You can combine data from multiple tables without using join, without using subqueries instead of using joins. Analyzing data at multiple levels of granularity. Now 10 hard-level SQL queries with subqueries. Below are advanced SQL queries that use subqueries to solve complex problems. Each query is explained for better understanding. Top N records for each category. Find the top 3 highest paid employees in each department. I will give you the content. Select department ID in the top 3 highest paid employees in each department. So first we need to see select distinct salary for employees E2 by hero department ID order by salary descending limit 3. This is the top 3 highest paid employees in each department. Employees earning above average in the department. Each employee earning more than the average salary of the chosen department. Employee ID, name, department ID, salary for employees E1. Where salary greater than select average salary for employees E2. Where employee ID could be department ID. In a subquery, calculates the average salary for each department. Autoquery filters employees who earn above their department's average. Let me know if you have better solutions to these problems. I'll be happy to answer your queries in the comment section. Please post your own level of approach, which approach you are using to solve this problem in the comments, and I will review it and reply to your comments. And I will also provide you with these SQL PowerPoints presentations which will be uploaded in my Google Drive or maybe GitHub. Detect duplicates in a table. Find duplicate entries based on a specified column. Select product ID from products, group by product ID, having constant greater than 1. Compare each row against the entire data set. Find employees who earn more than the employees in the sales department. Employee ID name salary from employees with salary greater than all. Select salary from employees with department ID equal to select department ID from department with department name equal to sales. Subquery fetches all salaries from the sales department at all greater than all ensure the salary is greater than the average value in the subquery. Rank without using window function. Rank employees within the departments. Select department ID, employee ID, salary. Select count star from employees E2 where E2 the department ID, E1 department ID and E2 salary greater than E1 salary as rank from employees E1 order by department ID, rank. Subquery counts employees with a higher salary in the same department. Rank is derived from this count. Find missing data. Identify employees not assigned to any project. Select employee ID name from employees where employee ID not equal to select distinct employee ID from project assignment. Subquery retrieves all employees assigned to projects. Autoquery filters those not in the list. Then we have compare groups across tables, self-referencing subquery, and employees who earn more than the manager. Employee ID name salary for employees E1 where salary greater than select salary from employees E2 where E1 dot manager ID equal to E2 dot employee ID. There is another way to solve this problem using join. Subquery retrieves the salary of the manager for each employee. Correlated subquery for percentage calculation. Select employee ID name salary percentage of total company sales salary for each employee. Salary into 100 divided by select sum of salary from employees as salary percentage of salary. Subquery calculates the total salary of the company. Autoquery computes the percentage distribution of each employee's salary. Dynamic threshold filtering we have. Then we have common table expression. CTE common table expression is a temporary result set in SQL that is defined within the execution scope of a single select, insert, update or delete statement. It allows you to create a named result set or reuse in a query improving readability and organization of complex queries. With CTE name you can give column 1, column 2, or maybe not. As select column 1, column 2 from table name where condition. Using the CTE, select star from CTE name where condition you can give. Simplify complex queries. Find the average salary for each department and list department with an average salary above 50,000. So with department salary, this is a city common table expression I'm using. Select department ID, average salary from employees from by department ID. Then we can select department ID, average salary from department salary, where average salary greater than 50,000. City department salary calculates average salary for each department. The main query filters department with an average salary over 50,000. Then we have recursive CTEs. Then we have using CTE for multiple queries. Then we have advantages of CTEs: improved readability, break down complex queries into logical steps with meaningful names. You can reuse the CTE within the same query while avoiding duplicate code. Better debugging, recursive queries, temporary table alternative, no need to create physical temporary tables in the database. Modular query writing promotes cleaner code by separating concerns. Use cases of CTEs: breaking down long and complex queries, performing recursive operations like traversing hierarchical data, reusing the same logic multiple times within a query, aggregating data from another sources. So CTEs are a powerful feature in SQL that can simplify complex queries, enhance readability, and optimize performance in many scenarios. Let me know if you want further clarification or examples. So that's all for advanced SQL topics, window functions, subqueries, and common table expressions. Let me know in the comments if you have any doubts related to this topic. I'll be happy to answer them, address them in the comment section. Or maybe I will post another video with a list of all your questions. I will collect all the questions that you have asked in comment section and will post those answers to those questions in the another video. Till date, happy learning, enjoy, all the best. And please like my video and subscribe to my channel. अगर वीडियो अच्छी लगी हो तो मेरे चैनल को प्लीज़ सब्सक्राइब कर दीजिए और वीडियो को लाइक कर दीजिए. थैंक यू सो मच.